So the solution is the error range. This graph shows how the robot should respond according to the program. When the error is between the -5 and 5, this part, the robot should move straight. If the error is more than 5, this one, the robot is on the black, so it should turn right. And if the error is less than -5, this here, the robot is on the white place, so it should turn left. The following is the power of the motor and a screenshot of the program. This can achieve what I said. This is its video. Analyzing the program, we find a problem of it. When the robot only drifts off a little of the range, it will turn significantly. For example, if the error is just 5, the robot will have a turn of 13, which is very big. But we want it to turn according to overshoot. So how to reduce the turn? The answer is the improved algorithm. Actually, the form is similar, but it has two situations. When the error is more than 3, the motor power is like this, so it will turn right to back to the line. If the error is less than -3, the motor power is like this one, and it will turn left. For instance, assuming the error is still 5, but this time the robot will have a turn of only 4.8, much smaller, right? So let's see the performance of the robot. Sorry for the direction. This time, I'll compare the 3 models. They are similarly close to the line. However, the speed of the robot with the original proportional controller is lower than that of the robot with the error range. So the error range works, but actually it still has a problem. The robot cannot exactly follow the target line. It may follow the line beside it. This is because its response is later than the detection, and the robot only has one sensor which can only give integer signals. So how to solve it? Our strategy is the integral. We add the integral to the previous model, and this screenshot shows how to calculate it. You may wonder why multiply 0.7. This is because when the robot is close to the line, the error is about 0, but the integral may not be 0. To make it close to 0, we multiply it by 0.7, which is less than 1. So it's just like the exponential function, it will be close to 0. These graphs can give you an idea about how the proportional integral controller works. And this is the power of the motors. Let me explain how this controller works. If the arrows are in the same sign, the integral will be big, so it will have a big impact on the robot. And it will have a big turn and back to the line. If the arrows are in different signs, the integral will be close to 0. So the robots will move straight or mainly depends on the proportional controller. Let's watch the video. From the video, you can see the robot is very close to the line, but you can also see it is very slow. This is because it has a limited calculating ability, which will limit the fundamental speed. Actually, we tried to increase the speed, but the robot will overshoot. Imagine the robot has good ability to calculate. Accelerate the previous video to give you the idea. That's all about our robot. Thank you for watching.